Our next reaction in chapter 19 is the aldol addition reaction. This is the addition of an enolate or enol to an aldehyde or a ketone. Your product is always going to be a beta hydroxycarbonyl compound. So if you take a look at the compound on the right, you have your carbonyl compound, alpha, beta, hydroxy. So beta hydroxycarbonyl compound. Now the mechanism of this is going to look a lot like what we've been seeing in this chapter so far. Your first step is going to be to react your base with your alpha hydrogen here to create an enolate. And then remember at this point that we have very little enolate and a whole lot more aldehyde that has not been deprotonated. That's why we're indicating two equivalents here. So the enolate can attack the aldehyde. So this gives us our intermediate. The new bond that we created was drawn in blue. The equivalent of the aldehyde that was attacked was drawn in purple. And then at this point, there's no leaving group on this carbon. So unlike in the Claisen reaction where we would reform the double bond and kick out a leaving group, we have to just go ahead and protonate. So we have a water molecule that was created in our first step. And that's how we get to our product. So this is called the addition product. The next idea is the Retro-Aldol reaction, which rather than being a reaction necessarily is more an acknowledgement that aldol addition is reversible. So once you've created your alpha beta hydroxy aldehyde or ketone, in this case a ketone, this is reversible in the conditions in which it was formed, and so you can actually undo this reaction. And in this case, when we undo the reaction, we would end up with two equivalents of acetone. Now, this idea is useful because if you have to figure out how to synthesize an addition product, it's useful to be able to analyze the bonds that would have been created in the aldol reaction. So in order to figure out which bonds were created, we look at the alpha carbon. We know that that carbon was the enolate, which means the bond that was formed is the bond immediately coming off of that. That means that this carbon must have been the carbonyl carbon of the other equivalent, and therefore this is our other carbonyl compound. Our next reaction is a continuation on the aldol addition. So once you've made it to the alpha beta hydroxy carbonyl compound, if you heat this up in acid, you can actually dehydrate that compound to create an alpha beta unsaturated carbonyl compound. It's important to note that this reaction is irreversible in the condensation reaction conditions. If you wanted to go from the condensation product to the addition product, you'd have to actually add in aqueous acid because water is a product in this reaction. So let's look at how this actually occurs. We are in acid, so we know that we need to protonate something. And that something is going to be our hydroxy group. And this is a common theme in organic chemistry. We know by now that the reason we would protonate a hydroxyl group is so that we can turn it into a good leaving group. So now that we have this carbocation and we have this carbonyl off to the right-hand side, the alpha hydrogen just became so much more acidic because if we pull off that alpha hydrogen, we can get rid of the unstable carbocation. And that brings us to our alpha beta unsaturated carbonyl compound. And our byproduct would actually be H3O plus because we picked up that extra proton. Now, aldol is very useful in synthesis because it creates a carbon-carbon bond. And we know that any reaction that creates a carbon-carbon bond is valuable because it allows you to take smaller, easily attainable, and cheap starting molecules and combine them into larger synthetic products. So this figure just shows us some of the possibilities that can be done using aldol chemistry. So we're going to start with an aldehyde, and in base, that's going to give us an aldol addition product, which is a beta hydroxycarbonyl. And if we put it in heat or add an acid and remove water, we will end up with our condensation product, which can undergo several different reactions. It could be reduced with lithium aluminum hydride to give an allylic alcohol, or we could go to the left-hand side and add in hydrogen gas and nickel under high pressure, and we can get rid of both the alkene and the pi bond to the oxygen and create an alcohol. We could add in hydrogen with palladium over carbon and get an aldehyde, so we would only get rid of the alkene through hydrogenation. And then you can also take that and reduce it using sodium borohydride. You can also take your aldol addition product and go ahead and reduce that with sodium borohydride, and you would end up with a diol. So there are a lot of different things that you can do through an aldol reaction. The main thing, of course, here is that you are taking a smaller organic compound and turning it into something that has a larger framework. So we're going to start with a fairly basic synthesis problem. We're going to start with ethanol and end up with N-butanol, or 1-butanol. So there's actually a couple different steps here. The first thing that you have to recognize is that our starting material has 1, 2 carbons, and our product has 1, 2, 3, 4 carbons. So we're definitely going to have to use our starting material twice. And being that this is the aldol chapter, I would probably start off with an aldol reaction. And then we're also going to have to figure out how to get rid of one of the oxygens and also get rid of all the double bonds that would be formed and retained in these reactions. So go ahead and take a second to think about it for yourself. You can also pause the video if you would like to work it out on your own. So your first step could be to go straight through an aldol condensation reaction, but I'm going to take you stepwise and have you do an addition and then a condensation reaction, just so we can get used to seeing aldol addition. So in order to get the addition product, we would want to add in aqueous acid or base. We're going to go ahead and use aqueous base. And typically you would keep this at a lower temperature to avoid the potential of dehydration. And this would give us the aldol addition product, 3-hydroxybutanol. So from here, we need to get rid of the hydroxy group because there is no oxygen on the 3rd carbon of our product. And to do that, our step 2 would be to have an aldol condensation reaction occur. So we're going to have to heat this, and a great way to do this would be to add in a strong acid, and that would give us our alpha beta unsaturated aldehyde, 2-butanol, and then in our last step we want to get rid of both the alkene and the aldehyde. And to do that, we could react with hydrogen and nickel under high pressure to hydrogenate the alkene and reduce the aldehyde to an alcohol.